Welcome to this video, and in this lesson we're going to do a simple introduction into the concept of tension. And tension is going to be a force that is created when you hang an object from a rope. And tension is always going to be away from the object. And so in this problem we're applying this basic principle of mechanics, and this is going to be an application of static equilibrium. We're going to use Newton's first law to solve the tensions. So the problem states that we have a 100 kilogram object and it's hanging from two massless ropes, and the ropes make an angle of 30 degrees from the roof. Find the tension in the ropes. So here's our object down here, this yellow box, and its two ropes are pulling away from it, and we'll pretend like this is the roof above here. And the first thing that we do when we have a problem like this is I always like to label whatever's inside of the box. Okay, so I like to put the mass inside here always, so I'm going to put always inside. When we have a box, I always want you to write the mass inside it so we know what we're dealing with later on in the problem. So there's 100 kilograms, and I wrote it a little bit to the side because we're going to have some forces here pretty soon. And I have these ropes here, right? So what I'm going to do is I'm going to, let's just assume that we're going to take a cut of, first of all, let me just define what we're doing here in terms of the object here. We're going to be defining a system around this object, which I'm going to show you here, and I'm going to do it with a dotted line. So I'm going to define a system here with this dotted line around this object, and this is where I'm going to cut the ropes here, and then we're going to make a free body diagram just of this system below. So now I've taken this same exact system up here, and I'm just taking this cut of the system here. And that's important to be able to take cuts of a system, because when we're taking a free body diagram, we have to define a system, and we're going to basically isolate all of the forces within that system here. So this is our system here. I'm just going to go ahead and delete that now. So we have two forces acting up here. So let me just draw my arrows in here. So I have my this is my to indicate my force arrows here. So I have the force tension here, and I have the force tension here. Okay, and I also have another force acting on this object. I have the weight of the object, which I'm just going to put straight down like this. And I'm just going to denote that as F sub G. Okay, now just a little side note over here. Side note. Okay. Okay, for tension, I always want you to use tension. I always want you to use F sub T. Do not use the letter T, okay? Don't use T like this, okay? That's bad news, okay? We have enough T's in physics, okay? We have tension, we have T for period, we have Teslas. There's so many different T's that why do we need to start adding more T's? I think that's terrible practice when physics teachers write the capital letter T for tension. It's just going to create more confusion later on down the road, okay? So let's use F sub T for tension, and then for weight, okay? Let's always use F sub G. Okay, I don't want to see you use the letter W, okay? Don't use W for weight. That's bad practice. That's lazy. Write the extra subscript in there. Why? Because W is west, W is watts, there's so many different W's. W's work. How many W's are we going to use in physics? It's too many. Okay, it's already confusing enough. Use F sub G when we're talking about the weight, okay? So I'm never going to be writing big T and big W and a big N for normal. That's another one. Let me just put that in there. Normal. Okay, I know I made a separate video on this, but my God, I just see people doing this, and it's just like they get confused. Write F sub N. Do not write N like that, okay? Don't write N for the normal force. N is north. N is newtons. There's so many N's already that we have. Why do we need to add another N? We don't. Okay, so always use the force sub tension, force of tension, force of gravity, force of the normal. Okay, so just stick with that format when you're doing this, and you're going to be a lot better off. You're going to understand the problem a lot better, okay? Just throwing that in there to help you have proper form, because form is very important. When you're trying to solve problems, remember, physics is difficult because every problem is different, right? You know, and when you do a math problem, I don't care what math it is. I don't care if you're in, you know, multivariable calculus, differential equations, partial differential equations. Once you learn how to do the problem, you can do about 90% of the problems, right? It's really not that difficult. But physics is completely different. And every problem is different, and you have to be able to set it up. So to be able to set it up, you need to have proper form when you're doing these problems. And if you have good form, you're going to have a better chance of getting the problem right. If you're here just scribbling and just writing things, and you know, I mean, I see a lot of students are resistant to even do a free body diagram, or they're scribbling doing proportions over on the side, or they're using x for every variable. You know, you need to get away from that, because that's the old way of thinking. That's when we were in algebra 1, algebra 2, and that's just not going to help you solve these problems. It's not good enough anymore. You have to change the way you think to go forward if you want to solve physics problems. Okay, so we need to learn proper form, and so this is part of it. We need to learn how to write the variables out properly. And another, you know, proper form here is always write your mass in the box. Okay, so write your mass in the box. Okay, that's going to help you out a lot. I know a lot of information here. I don't know all of it yet, because we said that we had this rope that was hanging by 30 degrees here, right? So I said this was 30 degrees here, and I said this was 30 degrees here, right? So we're going to use a little geometry here, right? If we have a parallel line here, let's assume that the top of this box is parallel with this line here. This is a transversal, right? And it's going to cut these two parallel lines, right? So we can use geometry to say, oh, that's alternate interior angles, right? 30 degrees, 30 degrees right there. So right away, we see the geometry of this problem. So in physics, there's a lot of geometry too, okay? 30 degrees. Okay. I'm going to add a little bit more, whoops, a little bit more down here. I'll rewrite this for form, since I'm on the subject of form. So put your mass in the box, which I just said. So this, and always label your axes. And I'll talk about that when we have a net force. It becomes a lot more important to label them in the direction of the net force. But I need to label them. Okay, so if it's a statics problem like this, I'm going to line them up. It depends on the situation, but I'm basically going to line this one up in the x and the y, because I want to line them up in the way that if I don't have a net force, I want to line my axes up in the way that the most forces will align along those forces. So in this case, it's a draw, right? They're all going in different directions. So if they're all going in different directions, let's just make it standard xy like this, okay? So there's my axes, okay? Now, what I need to do is I need to find the tension in both of these ropes. The first thing we're going to notice is that the tension is going to be the same. Okay, so tension will be the same in this problem. Why will tension be the same? Well, tension is going to be the same simply because these two ropes are at the same angle. Okay, now these are magical ropes. Okay, they don't have a mass, right? So this isn't important, right? If they had a mass, it would be different. The rope would be sagging, and this would have an extra weight in here, but it doesn't. They're magical ropes, right? So the tensions are going to be the same. So what I need to do is I need to resolve these vectors, or these forces, right? I need to resolve these into their components. Okay, so this object isn't moving, right? It's just hanging straight. So I don't have a situation where this is like in an elevator where it's going up and down, or it's jerking left to right, or it's not in a car, it's just hanging, right? So I have a pretty simple application here. So I need to resolve these tensions into their components, okay? So I need to resolve into the components. So how do we do that? How do we resolve an object into its components? Well, I have a couple videos up on how to do this. We have our angle here to the horizontal. So what I'm going to do is I'm going to take this blue line here to indicate this tension force here. And I'm going to show you that this is going to be force of tension sine of 30 degrees. Why sine? Well, sine is the y component. So when I'm talking about when I have an angle to the horizontal, the tension is the y component. I also have to draw an x component out here, which I'm going to draw out here by hand. So this is going to be ft cosine 30. Okay. Once I've drawn these two resultant components, we need to get rid of this component. So there's a couple ways you can do that. If you're writing in pen, what you can do is you can just draw an S through that to strike it out to show that that force is no longer there. I've now resolved these into the two components, and so that's our goal. So we don't want to have an illusion in a problem that we still have three forces here, right? Because once I've resolved this, there's only two left, right? Okay, so that's the first part of this. Now the next part of this is I'm gonna circle this in a different color over here, red. So this tension here, we're going to do the same thing. We're going to resolve it into its components, right? And so this one, I'm going to go ahead and I'm going to draw it up about the same length, because it is the same length, right? And I'm going to draw it going in the same direction here. So I'm going to draw ft sine of 30. And then I also have a component over here that is this way, which is going to be ft cosine 30. So there we go. Now we have these two forces. I'm going to strike that out, right? So however you want to do it, you just kind of strike it out like this. I have these two forces now resolved into their components. Even though they're the same magnitude, I just drew them in different colors so you can see it. Now I need to take care of this business down here about my weight, or my force of gravity. In this case, we know what's the force of gravity. It's just mg. So the force of gravity is going to be 100. How did I know that it was 100? Because I look into the box. The box is going to tell me, right? And then I'm going to multiply this times. We can just, in this case, let's just do 10. Okay, g is 10. So g, g, if we're talking about gravity, gravity is, we'll just use g is approximately 10 meters per second squared. I'll just go ahead and approximate it in this case. I normally don't, but we'll just go ahead and do that. Not a big deal. So now I can see right away that this box is 1,000 newtons. Okay, that's the weight of the box. Okay. So what I would tell you is as much as possible, work with your free body diagram before you even set up an equation. Try to solve as many of the forces as you can on the free body diagram before you even go to an equation. Okay? It's going to help you in the long run. So now I have a really clear picture here. I have my up forces, I have my down forces, I have my right forces, and I have my left forces. So this is a perfect example of this example right here is going to be Newton's first law. And what is Newton's first law? Anybody know what that is? Newton's first law is the law of inertia. So it says an object will stay at rest, or it will stay at motion, unless there's a net external force acting on it. So what that means is basically, if an object isn't moving, it's going to take a net force to get it moving. Now that doesn't mean there's no forces, right? We can see very clearly here there are forces, right? But none of them are. It's a draw, right? It's a stalemate. It's gridlock. They're all in balance, right? So basically, Newton's first law says all of the forces are in balance. Forces are in balance. Okay, so they're in balance here. So when we have this situation, we can go ahead and write simple equations here. Now I'm going to start out with the sum of the forces in the x, even though we're not really going to use that. But the first law basically says this: the sum of the forces, I'm going to put it in the x, equals 0, right? And I'm going to put this over here. I'm going to say the sum of the forces and the y equals 0. So why do we split it up into two equations like this? Why can't we just say the sum of the forces? Because the only way to say the sum of the forces equals 0 is to show it in a picture like this, because they're vectors, right? So my original picture here, tension, tension, gravity, that was the sum of the forces equals 0. We need to resolve it into components. And we do two equations because usually we're going to have two unknowns. In this case, I only have one unknown. So the x equation isn't really going to help me too much. If I wrote the x equation out, what am I going to see? I'm going to see this ft cosine 30 and this ft cosine 30 here. So there's not much information in that equation. When I have, also going back to Newton's first law, when I have this situation here, we can do a nice little shortcut. Since it's in balance, I can say whatever's in the left is going to equal whatever's on the right. It's like a scale, right? Everything's in balance. And when I have the sum of the forces in the y, I can say whatever's in the up direction equals whatever's in the down direction. So it's a nice thing that you can do to simplify this, okay? So what's in the left here? I have ft cosine 30. What's on the right here? I have ft cosine 30, right? So I have ft cosine 30 equals ft cosine 30, right? Is that really going to help me that much? Not really, right? So that just becomes 1 equals 1. I have a simple reflexive property, right? We don't really use that in physics too much. We use it more in geometry when we're trying to solve proofs with triangles, say if they share a side, but this isn't really going to help us much here, right? So let me go over to this side here. Let me go over to what's going on. So I have the sum of the forces up. The ups equal the downs. So here are my up forces here, and here's my down force here, right? So let's go ahead and write out that equation here. So what are the up forces? Well, I'm going to write it in colors this time. I'm going to have to help you see this, because I'm going to say ft sine of 30 plus ft sine of 30, and we're going to write it in black now. We're going to say equals fg. Okay, so the ups equal the downs. I should put plural on this. The ups equal the downs, right? So I only had 2 in the up, 1 in the down, so they're in balance, right? So notice these are both the same exact force, right? The same exact angle, same exact force. So I'm going to combine these now. So if we're just doing some simple algebra here, I'm going to group my terms. I have 1 here and 1 here, so I'm just going to write 2 times ft sine of 30 equals fg, right? And we know what fg is, right? It's 1,000, right? So I can begin right away solving for this now. So I can, let me just go ahead and plug in that number there. Even though I normally don't like to plug in numbers until the end, I'm just going to do it in this example just to simplify things here. So 2ft sine 30 equals what? Equals 1,000. See, it's better practice, it's better form not to plug in the numbers as you're going, and it takes a little bit of work, but you get used to it. But in this example now, we're just going to solve for my unknown, right? So what is my unknown? Well, my unknown is the tension, so I always circle my unknown. Whatever I'm looking for, I want you to circle it. That's what we're looking for, right? So in this point, right, I can go ahead and start to solve. I can say ft, right, equals 1,000 divided by 2 times the sine of 30, right? So in this case, I can go ahead and tell you that's a very basic problem to solve here now, because I know that I have 1,000. I'm just going to go ahead and write these in black now, my final answer. Sine of 30 is 1/2 times 2 is 1. So it's just 1,000 over 1. So my force of tension is simply going to be what? My force of tension is going to be 1,000 newtons. Okay, so in this particular case, let's throw a box around it. The tension in the rope was equal to the weight. Okay, so that's a very simple application there of Newton's first law. Hopefully you understand now how we were able to do this by going through the step-by-step process of labeling our free body diagram and then applying Newton's first law and then doing our simple application here to the ups equal to downs to solve for the tension in the rope. Thanks for watching.